there are quite a few people on Zoom, especially people who may find university. They kind of on Zoom. That's all right.
Yeah.
Maybe I will probably start with that. Okay, all right. Well, I guess it's fashionably late, 12:05. So let's actually get going with this one. So this is joint seminars on the biostat at the Fred Hutch and University of Washington. So we have some people on the Zoom. So, but anyways, welcome. I want to sort of quickly sort of make sort of overall kind of comment, as you probably know that everybody probably here in this room using the LA large language model one way or another. And of course, we also know that the huge amount of money is being invested into large language model, AI, and so on and so forth. And of course, in this institution, there are some series of the seminars and workshops that being kind of being devoted to the AI thing. But I think one of the particular sort of the area that really should a lot of attention essentially is a large language model in various different sort of applications. So just in terms of dollar cents, the total amount of funding to invest into NIH is about $48 to $50 billion a year. Do you know how much money being spent by Google in the AI? It's about $70 billion. Okay, and then collectively in the field of the field of the AI 2025 about $250 billion. So you can see the scale of this development, and is just huge. And of course, this is even though AI have been around for long, actually for quite a while, we've been sort of encountered in one way or another. But the large language model as sort of new branch of the AI is sort of kind of take over. So essentially, the most people think of AI as this large language model. And of course, I kind of agree. This is the inflection point. It is actually probably probably in the next few years, it will be part of maybe driving force there for moving forward. With that being said, and so for this is sort of the joint system, typically we always have a senior biostat faculty members to give sort of kind of overview on the topic of the interest and so on. But large language model is really new. I mean, really, there's not a whole lot of senior members that I can see, but we're fortunately getting a really sort of young, bright start from Google and Dr. Palepu. So obviously, you can see he's very young, but he got his bachelor and a master in biomedical engineering in Johns Hopkins. And he worked on various clinical applications of machine learning, including epilepsy, localization, EEG, surgical instrument tracking in video, and precision embolization catheter development. And then he went on the Harvard MIT Health Science Technology to complete his PhD. His research focused on characterizing and improving self-supervising imaging text models in medical applications, including topics such as the local alignment and shortcut learning and conformal predictions. It's all very interesting topics. Today, Annie is a research scientist at Google, where he works on large language model as the specific assistance for biomedical application. Since the May 2023, he has now become a core contributor to the AMIE. I'm not sure for people who don't know, is the Articulated Medical Intelligence Explorer. I came across it from the Nature. I was so impressed into what they try to do. The project focuses specifically evaluating diagnostics and management reasoning for this systems in medical conversation settings. His work primarily focuses on improvement of the systems through various methodologies and uses synthetic data generation and modern post-training agent design and then large language model-based audio evaluations. So it's, to be honest, I mean, when I see this one, I thought, wow, this is going to change the world. We've been working hard to try to improve the precision of the AI and so on and so forth, but they are actually really looking at it really to transform the medical practice. Now, of course, there's a long way to go, but nevertheless, they are doing that. I mean, I was so impressed, so that's why I have Anil come over to tell us what they want to do. Sure.
Yep. Thank you so much for the kind introduction. Yeah, as mentioned, I'm Anil Palepu. I'm a research scientist at Google Research. I've been working with this team, AMIE, for the past 3 years, and right, the point of our project is to try to, in a more meaningful way, evaluate these conversational AIs in terms of their diagnostic and management capabilities. And I'll talk to you a little bit about how we did that. Uh, but to start, first of all, I want to go over a little bit of background on LLMs in medicine, and I'll do a very brief overview. There's plenty of research in this space that I won't get to talk about in this talk. Um, and then I will talk you through 3 different papers of sort of increasing complexity. The first, where we basically ran a randomized blinded study to assess the performance of our system in a OSCE type setting where it's talking to a patient actor and providing diagnoses. We extended that to disease management, to longitudinal disease management, where we're managing a patient over multiple visits. And then finally, we tested that in a real clinic with 100 patients at Beth Israel Hospital in Boston. Towards the end, I will go over some of the future directions we've been working on and already are working on, and some conclusions from this talk. So to start, so here, when we talk about AI, we're talking about LLM-based systems, large language models, and these are general purpose foundation models. So the advantage of this being that, these models, rather than, some of the prior models that came before it, really are capable of a variety of things. We don't necessarily need to train this model to perform one single task, but rather by training on a very large corpus of broad varied data, these models are actually able to generalize to a wide variety of tasks. And the specific models are autoregressive decoder-only transformers. Autoregressive meaning that they generate tokens sequentially, and those tokens are put back into the inputs to generate the future tokens. And this language model is essentially a probability distribution over these tokens. So given, a given input, the model learns, what is the most likely next token, and sort of recursively is able to generate outputs. This is typically not done in like a greedy manner where it will simply, choose the most likely next token every time, but there's some algorithms used to maybe more intelligently sample from the model at inference time, beam search being the example here. So when we talk about training these models, I like to kind of classify these into 3 main groups of training. So the first is pre-training, where we essentially shove, internet scale amount of text to the models, and we have it perform this next token prediction to basically learn from this large and varied data. And in our work, and like most people that work with these models, we don't really do this pre-training ourselves. This is something that will be given, and we might be building on top of a pre-trained Gemini checkpoint in our case, or whatever competitor model. So the other 2 stages, supervised fine-tuning and reinforcement learning, comprise the post-training stage of the model, where you're really refining it to perform, the particular task that you want to be able to perform. So supervised fine-tuning is essentially where you are, providing the model with, instructions, particular examples of inputs and outputs that you want it to be able to do. And this in particular is quite useful for instilling things like instruction following, dialogue-like behavior. Like if you had just taken a pre-trained model, it probably won't talk to you like ChatGPT does. But some of these steps help instill that sort of behavior. And then reinforcement learning, where this is a slightly different paradigm, where instead of directly telling the model, this is the correct input and output pair, you actually sample from that model, many trajectories, and you have some mechanism for understanding which trajectories are good or bad. Sometimes that's like a reward model, which is trained based on human preferences. There's other methods that use certain automated feedback or machine feedback. But essentially, the essence of this is you're able to reward good trajectories from that model to make it more likely to produce those similar trajectories in the future. But so you don't stop at a train checkpoint. At the point when you have trained your model, your LLM, there's a lot you can do on top of that to really get the most out of it. I kind of am simplifying this quite a bit, but I think three sort of categories of things that are done at inference time. So one is, thinking or chain of thought. And here, the finding here was basically that models tend to perform quite a bit better when you allow them to emit intermediate reasoning prior to the final response. And now, like, this is actually something that happens natively when you talk to any of these models, in their UIs, but previously was actually something that you had to, specifically try to elicit. And this extends, I think, to other applications like, potentially like drafting multiple responses and synthesizing those responses. The essence is basically by spending more time at inference time, you can actually typically get better responses. Another class of techniques, tool use and function calling. So these models, by themselves, they only encode knowledge from, when they were trained, but there's a lot of information that, you might not want to rely on the weights of a model to actually perform. And so these models themselves can, write code and execute the code. These models can, access tools like search and, bring in external knowledge where relevant. For example, in our work, we deal with, medicine where the clinical practice is constantly evolving. And so being able to reference these updates to clinical practice guidelines is quite helpful. Whereas if you were to use a model trained in 2023, it might not understand, modern medicine. And then finally, this has been, quite a popular topic recently, AI agents. So the idea here is you can actually compartmentalize, different units of these systems, and each of these units might have its own internal state, its own logic for what it's supposed to do. But these units can actually, you can actually use like many of these units collaboratively to tackle, more challenging goals. So they can themselves perform these tasks long range autonomously, based on, their design of that agent. So that was a little background on large language models and their training and their inference. But a big question that we had on our team, and many folks have as well, is how well do these systems work in clinical applications? And there has been a lot of research on this at Google, and particularly trying to improve performance in these domains, showing some of the examples here. And the basic essence of this line of research has been around trying to show some kind of expert level performance on medical benchmarks. So on the left is a graph showing this MedQA performance. It's like USMLE style questions, multiple choice questions, and showing that, the perform. And this was actually, several years ago already, but performance on this benchmark is climbing. There's a lot of caveats to these results, and questions about, was this in the training data, things like that. But the basic essence is, a lot of research has done this type of work. We're showing, medical capabilities seem to be climbing in these LLM-based systems. From our team, we've looked at this specifically for differential diagnosis, and so we had a paper, 2 years ago, which was looking at the diagnostic accuracy of these systems on these very challenging CPC cases. So we tested a few different arms in this interface. So one was a clinician interacting with our system and trying to come to the differential. Another was the clinician interacting with search, and then finally the AI acting alone. In this case, in this particular subset of cases, we actually found that AMIE by itself had a very strong standalone performance, as well as a very strong assistive effect when used by clinicians to aid in forming their differentials. Again, many caveats and limitations to the scope of this study. Sorry, what? What's the reason for the yellow line below the right line? I think so. So I think the question here is like, are clinicians able to effectively use our particular instantiation of an AI assistive system? So there's many explanations. Like the one explanation is clinicians like are not able to effectively use our system, and that could be because of an issue with the way it's implemented in the study, or it could be an issue of basically like them not being able to effectively, use this type of system. I think uh, essentially having this type of system was not as useful as in just generating diagnoses with the system by itself.
What is accurate? What's your gold standard?
Yeah, so the gold standard here is a specialist rating the quality of the differentials. And so, and I'll talk more about this type of graph later, but this top K accuracy refers to, for a differential, if you truncated it at the first three diagnoses in the list, how often was the correct diagnosis within the first three items in that differential? Triplicate ratings. Triplicate ratings. Yeah. So 3 clinicians, and you take the median of their ratings. Okay, so these results are interesting, but importantly, the prior results dealt with static benchmarks. So these are cases where all the information was already available up front, and the task was basically synthesize this information, come to a conclusion, whether that be, an answer to a multiple choice question or, a differential diagnosis or something of that sort. In the real world, clinicians are not given all the information up front. They're met with a patient who they may know very little about. Maybe they have some information on them up front, but essentially they need to talk to the patient. They need to elicit the right information, do so in an empathetic manner that makes the patient willing to share that type of information. That's useful for them forming their diagnoses, forming their differentials, forming their investigations and next steps, and manage this patient over time. And so I really like this quote. The medical interview has been termed the most powerful, sensitive, and versatile instrument available to the physician. So the question that we ask in our line of research is, great, these LLMs seem like they have some medical knowledge encoded, but how well can they actually elicit this information from patients and get the information needed to even use this medical knowledge in the first place? So to conduct this research, we adopted a framework called the Objective Structured Clinical Examination, or OSCE. This is a validated assessment format that is used in many medical schools to assess, trainees. And essentially, the design that we'll be talking about in many of the future studies is you have a simulated patient. The simulated patient is a patient actor who is given a particular scenario pack, and they're trained to enact that scenario pack consistently. And that scenario pack will include information about, this is the information you should share up front. This is the information you should not share until you're asked. And these are, all of your demographic details, your history, things like that. So that simulated patient will talk to one of either a PCP or our system in a randomized blinded sequence. And they will not actually know who they're talking to, theoretically. Of course, in certain cases, it does become a bit obvious. But they'll have this conversation, and in the end, we'll have some artifacts produced by either agent as well as evaluations from specialists to understand the quality of the conversation, the quality of the recommendations being made in either case. So before I get into the research, I think to step back, I think what I want to claim with this work, first of all, is we have some preliminary evidence that AI has potential in diagnostic dialogue through meaningful randomized evaluations, and we've learned some generalizable methods and learnings for understanding and improving AI performance in this domain. What this presentation is not claiming is that we do not have proof that AI doctors are superior or can do the job of real doctors. This is, one limited scope of, what doctors need to do. And also, in this work at least, we're talking about a text interface, which is not reflective of real clinical practice. And this work will not really get into the kind of sample size and large scale evidence you need to really demonstrate robustness and efficacy, on a larger scale. Okay, great. So the first paper towards conversational diagnostic AI, this is the first work we did, which demonstrated in this OSCE setting, the competence of this particular agent. At the time, this agent is actually built on PaLM-2, which is a much older model. And I'll talk you through a few of the steps we used in developing the agent before I get into the study. So as I mentioned, one thing we do is supervised fine tuning. In this case, we had this PaLM-2 model, which was fine-tuned on medical data. So various medical reasoning, the medical question answering type data sets, as well as real world dialogues it was trained on. And finally, I think most importantly, simulated dialogues, which mimic what a doctor-patient conversation might look like. And at the time, this was quite important because especially when you look at models like PaLM-2 that were very old, they were not able to conduct this type of conversation natively. Even with any extensive prompting, they were not able to hold a conversation over, several turns and kind of maintain that context. Another important aspect is auto-evaluation. So in developing the system, it's quite useful to have some measure of how the system is doing at any given point in time as you continue to develop it. And while it's great to get clinical raters to do this task, at the scale of data that we're talking about, it's not quite feasible to do that for every dialogue that we produce. So in development, we use auto-evaluation. So this is actually LLM-based auto-evaluation where you can produce intermediate ratings for the diagnoses that your model's producing, the turns that it's producing, and that can actually be fed into the iteration to basically guide some of the training. As for the actual dialogues that were produced, we did this by simulating conversations between an AI agent, the doctor agent, and another AI agent, the patient agent. So the patient agent was conditioned on these synthetic vignettes. The vignettes were drawn from, were actually synthetically generated themselves, but drawn based on search results. So, for any given condition, understanding what are the demographic makeups of people that tend to have this condition, what are the typical symptoms, what are example, histories for patients with this type of condition. But ultimately, all that is synthesized into various vignettes, which the patient agents are conditioned on. They have a multi-turn conversation that turns into a simulated dialogue. And we also have a separate agent, a critic agent, which is able to critique the performance of the doctor in that simulated dialogue. The reason for that is, when you just let two agents talk to each other, sometimes it might turn out okay, but most of the time it will not. And you needed some kind of feedback loop to say, hey, the doctor did not ask the right question in this case. They did not ask for a certain, set of history that they should have asked. Feed that back to the doctor and let the doctor try again. So it's kind of like this is completely at inference time, by the way. Refining the doctor's performance in that particular conversation. But so through this process, we're able to simulate, many, many dialogues. And these dialogues are part of what, went into this previous step, this fine tuning. So we are basically providing PaLM-2 with some examples of what a good doctor response would be in various conversations based on our simulations. And it's learning to do that natively rather than through this intensive, curated simulation process. Okay, so that's how we developed this agent. And in terms of the study itself, we worked with 159 scenario packs with ground truth. And these were sourced from the UK, from partners in India and Canada. We had 20 primary care physicians for comparison with AMIE from both Canada and India, and 20 patient actors 23 specialist physicians to perform ratings. So these were categorized, the different scenarios were categorized across a few different specialties. And we had, specialist physicians rate the quality of the differentials and recommendations.
Class rating?
The 20 primary careers for top class, they were debatable. I think we had the specialists review their conversations, and they were, I would say, consistent with what would be expected from a primary care physician. I don't know if I would call them specifically. They were all vetted, I will say. So we do vet them all to make sure they meet a certain quality bar. But yeah, top class is a bit of a subjective term as well. Yeah, so then, to remind you, this is kind of the study design where we have AMIE or the PCP interact with the simulated patient. And so the simulated patient will talk to one of them, and then afterwards they'll talk to the other one, and they don't quite know which one is which necessarily. So after they have the conversation, the patient actor will answer a post-questionnaire, and this will involve, their interpretation of the conversation, and so some different aspects of this, like how empathetic was the doctor? Did you feel heard? Would you see this doctor again? So these are qualitative questions rated on a Likert scale from 1 to 5. But we use this to try to understand how, of course, with the caveat that this is patient actors, how a patient might feel in this setting of talking to this AI system. Then from the PCP and AMIE side, we have them produce, after the conversation, their differential investigations and treatments they would order at that point, and any escalation follow-up that's needed. And finally, we have the specialist physician look at all these artifacts. So they look at the full scenario and the ground truth. They look at the conversation that actually happened in each arm. And they look at the post-questionnaires from the PCP and AMIE, and they evaluate a few different things. So they evaluate, that DDX accuracy, which I showed you a plot of earlier. They also evaluate some more of these like Likert scale questions around the quality of the history taking, the quality of the management, and things like that. Quality of communication. So in this text-based setting, we found that AMIE produced more accurate differentials than the PCPs. And so to remind you of this plot, on the bottom axis, we have top K accuracy. So for a differential of, let's say length 3, if you truncated the differential to the first 3 items, the PCPs had closer to 75, the AMIE had closer to, 87, something like that, percent of the time that the ground truth diagnosis was present in their differential.
You can help to define top K. What are you supposed to mean? Because I think most people have nothing to do with that.
Yeah. So top K is basically like truncating the differential at different lengths. What proportion of scenarios did each agent have the right diagnosis in that? So like the maximum here, 10, means if it listed up to 10 items, and in many cases they would not list 10 items. But if you took up to the top 10 items that listed as differential, how often was the ground truth present in any of those top 10?
Were these complicated scenarios? You didn't comment on anything about what the general.
No. In general, these were common presentations of common diseases. And these were not something that we worked with partners that actually do this kind of scenario generation for training themselves. So we didn't like pre-specify we need these specific scenarios, but that tended to be what we got, mostly common presentations of common disease.
Specialists reviewing clinical exam skills, practical assessment of clinical exam skills. And was AMIE doing an exam, or it was all just conversational, right?
Yeah, not physical exam. This gets into some of the aspects of history taking. I'll show you like what those criteria. Yeah.
Information provided.
are people coming in with these pre-existing diagnoses up to 10? Or are those different potential diagnoses being generated by the physician?
I'm sorry, I'm not sure I understood the question.
Or the new diagnoses and the physician or physician are generating multiple possible diagnoses to different.
Oh, so the patient in this scenario has some presenting complaint with some associated diagnoses for that presenting complaint, and they in the scenario packet they might be a patient that does have some pre-existing conditions, but the performance here is, are you identifying the the diagnosis in question for that was this scenario was designed around.
So they're generating that.
Yeah, so AMIE is generating a differential, PCP is generating a differential up to 10 potentially. Yeah.
Differences in the number of potential diagnoses generated.
There were differences. AI in general will produce broader, longer differentials. The top K metric does control for that by truncating. So you can look at any individual but if you start to look at like 10, very rare that a PCP will output 10 items on the differential. But I think that the lower numbers tend to be a little bit more meaningful. Okay. And yeah, so continuing on this topic, like there were differences between the ways that AI and PCPs conduct their conversations, and this is not unexpected. So the main difference was, how long their responses were. So, AI, if you've talked to a chatbot, will output a lot of words, and it will, say a lot of things. And that middle plot, you can see that pretty clearly. The number of words being output in any given conversation was a lot higher than, what the PCP was outputting. That being said, the total amount the patient actors were saying in response to those messages was very similar. So the idea there being that we don't have clear evidence that the patient actor was giving the doctor any, more amount of information, rather that the models were just being more verbose. And similarly, like a similar number of turns. So it's not like this was a longer conversation necessarily, in terms of number of turns. And I think the really interesting ablation we did was we gave AMIE the conversation from the PCP. So we basically had it produce a differential using the conversation the PCP had. And what we found here is it actually was, equal, if not better, when using the PCP's conversation. So what this tells us is that, like, we're not seeing, any kind of superiority in terms of the conversations themselves, but in producing that differential list, it is ranking the ground truth differential more accurately than the PCP did in this setting. Yeah, and then so these are some of the criteria we asked, from the patient actor perspective. A lot of these are a bit similar, but they come from, these validated scales, being polite, making patient feel at ease, listening to the patient. These come on a Likert scale, so from very favorable to very unfavorable. And, we had the patient actors rate how much they enjoy the conversation. Obviously, many asterisks here that these are patient actors, not real patients. And, I think in some cases, potentially biased by the length of responses and, the willingness of AI to say a lot more and really acknowledge every statement you're saying. But that being said, this is encouraging to see that patients were happy, the patient actors were happy with the experience overall. And from the specialist physician perspective, many of these ratings, so this across a few different criteria, I'm only showing a subset, but relationship fostering, gathering information, providing information, decision-making, enabling disease and treatment-related behavior, responding to emotions. Again, these come from certain validated scales that we discuss in the paper. But essentially, here, the AI is also rated quite favorably on these scales by the specialists in each domain. Plenty. Yeah, so we did 159 simulated patients. The number of unique patient actors who were acting out those, so like one patient actor might be given, multiple scenarios to act out. But they're trained on each scenario that they enact. Yeah, so we had 70, I think it was 75 India scenarios, and Indian patient actors acted those out. So Indian scenarios meaning the lab in India that develops these OSCE type scenarios developed 75 of their scenarios for us. And then similarly in Canada, we had the Canadian patient actors act out those scenarios. Very expensive, yeah.
I'm wondering, you're kind of combining there's multiple steps that need to happen to kind of reach a successful differential diagnosis. I'm wondering, are you grading the sort of intermediate steps in some fashion? Like, for example, if you want to get the best differential diagnosis, you need to extract all of the relevant information in the simulated patient packet.
Yeah.
Are you grading in some way how accurate, what percentage of different facts are being extracted?
Yeah, so I can answer this in two ways. One is, in these specialist ratings, we do ask, for different sections like, medication history, like different aspects of the history we ask. But again, that's not perfectly granular. That's still on like a Likert.
I mean, certain things are really critical.
Yeah.
There might be certain facts. It's like, if you don't get this, you can't reach the right
Yeah.
diagnosis. Like, is there some grading? Like, these are the critical pieces of information. These are sort of like supportive, nice to know, but not critical to reach the right diagnosis. Then everything else is just noise. And then, is there some separation of this is most critical, this is helpful, but not 100% necessary, and then this is just toss it out as noise? Yeah.
So in these scenario packs, we do have so this is something that's given to, we don't have ratings for each, but the OSCE scenarios often come with a checklist of sorts, which will enumerate, for example, very particular questions that should be asked. And that is part of what they're using when they're evaluating, but we don't actually have granular, check boxes for these scenarios. And that was mostly, I would say, a decision based on time, and investment, and how long this evaluation process takes. Yeah, I'll do one more question, but I do want to get through more of the precision. Yeah.
And so what you're evaluating is competency rather than the diagnostic of the process. So just a quick question: what diagnosis? What was true scenarios? What are some examples?
One is celiac disease, and there were, and so the ground truth there might include the specific.
So if you just give us a list of diagnoses, have a sense.
Yeah, so in the paper, there is actually a list of all the diagnoses. There's a table at the very end that includes the list of the full, ground truths. Yeah. Yeah, but as I mentioned, typically common presentations of common disease was the distribution. Okay, so, and that's actually the first limitation. So mostly common presentations of common disease is the first main limitation of this. Also, this is not an interface that is reflective of real world practice. This is a synchronous text chat, whereas in the real world, you might be looking at a patient physically and observing what they look like and, how they sound to make your recommendations. A lack of workflow integration. So this was evaluated as standalone chatbot, whereas, there's no access to history, there's no access, to their medical record. It was also a single visit snapshot. So we're only really evaluating a patient that you know nothing about to start with, and does not address longitudinal care. And then also, again, this is a simulated setting with patient actors who may or may not perfectly behave like, a realistic patient in this setting. So I won't talk about these works in too much detail, but I do want to just briefly say that we are trying to explore, some of these limitations in some of our work. So we have some studies exploring, reasoning in subspecialty domains, two of which I've listed here. We have some work exploring performance in multimodal settings in two particular settings. So one is where the scenario specifies, a clinical image that they might be uploading during the course of the conversation. Another is moving away from a text interface to a real-time, FaceTime type interface. In terms of workflow integration, this is, I would say, quite underdeveloped, but we have explored one potential clinical workflow we call asynchronous oversight, where the intake is happening, withholding from giving any medical advice, but then that information is passed on to a physician after the fact. But the next study I want to dive a little bit more into is this single visit limitation, where we ask this question: can AI manage a patient longitudinally? And also bringing in another component, which is the clinical practice guidelines. So previously, like the ground truth, maybe was rated on these Likert scales, 1 to 5, and it's unclear, like, 5 means, okay, good quality, but it's not really getting granular at all. And here we want to understand, like, how well specifically is it adhering to very particular recommendations that might be present in the guidelines. And so the study was designed kind of extending upon the previous study, where you had multiple sequential visits described in the scenario. One major limitation here is you're assuming a certain trajectory for this patient. So regardless of what happens in visit 1, you're going to say, okay, they're going to get this particular test done, even if the doctor in visit 1 did not order that test. But that's sort of a necessary constraint of designing this kind of scenario. But essentially, they have these sequential 3 visits. In each one, they have a conversation. And these, they provide, the same post questionnaires. They're evaluated in a similar way, except this time each scenario the recommendations were based on, 1 of 2 sources. So these NICE guidance and BMJ best practice. So these are actually UK-based recommendations, and so some caveats there. But the point is, given a source of ground truth, how well can these models adhere to that particular source of ground truth? And from the agent standpoint, one development we had was moving away from a single agent architecture to a multi-agent architecture. So similarly to before, we have this agent which is talking to the patient, but now this agent has an internal state. And this internal state is basically behaving like its memory. And it's managing what the agent currently thinks, the differential, their summary of the patient and things like that. But this agent is sort of meant to be very fast and very quickly respond to the patient as soon as the patient says anything. On the other hand, we have this other agent, the MX agent, and its purpose is to be the reasoner. It's meant to do the deeper research, to think deeply about the problem, but not be latency constrained, because this process of looking through a bunch of clinical practice guidelines and drafting plans and refining the plans might take a long time, and a time that doesn't really work out for a synchronous conversational chat. So essentially, this will help generate a management plan, and that management plan can be used by the dialogue agent, but it is not gated on having the most up-to-date plan at any point when it has to respond. Okay, I will skip over some of the details in the management agent. But essentially, we evaluated the system across multiple visits. And so, the initial visit might be, what is your initial differential? What investigations you're going to order? The second visit, you might need to adjust the treatment due to some complication that's occurring. Third visit might be, something beyond that of communicating with the patient. And there's different, things each scenario was designed around, again, by our partners. But essentially, when rated by the specialist in the same way, we did see some, promising results in terms of how we lined up against the ratings of the PCPs. I think the ones I really want to highlight are, the precision. So having access to the clinical practice guidelines, the agent being able to reference them, helped make them quite precise in their investigations and treatments. And also, also like alignment with guidelines. So, when given that particular source, it's able to provide recommendations that are aligned with that source as well. And we'll also skip this quickly, but just to say that we also tried to evaluate, in particular, the medication reasoning. So, we did this by generating a benchmark that was vetted by pharmacists to assess basically the medication recommendations of this agent, and assess its performance both without access to anything as well as ability to reference medication labels from the internet. So the final study I want to dive into, so all of this prior work that I've discussed has been with simulated patients, but there's a big question here, which is how well do our results with simulated patients translate to real patients where, any number of things can happen, right? And so in our next study, we worked with, a single center. So this is a single center feasibility study with Beth Israel Hospital in Boston. And we were basically working in an urgent care setting where so a patient basically had an upcoming urgent care visit. Prior to that visit, they would talk to our agent. The agent would be told, not to provide explicit, differential management, but rather it was able to provide potential things you might hear from your doctor. But this was, guarded against, basically prescribing any kind of, official recommendations. And each conversation was monitored synchronously by a AI supervisor who was a clinician at the practice. So this is, again, a single center feasibility study, 100 patients. We do plan to, expand our studies to a more nationwide randomized study, which can help build evidence further, but the work here is a little bit more limited. And yeah, so the primary endpoint here, we were simply looking at the safety of the system. So where there were some pre-specified safety criteria for why this conversation might need to be terminated. And the primary endpoint was basically, did that happen at all in any of these conversations? As well as what was the dialogue quality, patient and PCP experience from these conversations. And this was a pre-registered trial, clinical trial. So, the agent in this setting, a lot of the similar paradigms that we've talked about before with an internal patient state. I think one important addition was this explicit phase transition, and this is just one version of this. There's of course many ways you could design this agent, but we had it actually explicitly walk through a certain set of phases, and its behavior and logic in each phase was variable. So like the prompts it's using in the intake phase will be very different than the prompts it's using when wrapping up the conversation. That helps customize the behavior at different stages of the conversation. So the study design, they would have a text chat with AMIE. They would have an in-person provider visit 0 to 5 days later. And then, a chart review and evaluation. So 8 weeks later, this was done to basically adjudicate what was the quality of AMIE's, conversations, diagnoses, recommendations. So during this, synchronous chat, the AI supervisor was watching the whole time. Anytime they would have feared, any safety issue, they would have terminated immediately, and talked to the patient to, clear up any confusion. The PCPs were given access to AMIE's chat transcript and summary, and they were able to use that when they talked to the patient subsequently.
And the patient, they knew AI, they chatted.
Yeah. Yeah. So the patients were consented and they understood the process they were going through. In the paper, we get into the distribution. It's pretty reflective of this particular practice. I will say that those who consented might not be perfectly representative because they might trend towards people who are a little bit more tech savvy, maybe a little bit more health literate, who are willing to even go into this kind of process. But yeah, I don't have that off the top of my head, but that is in the paper. Yeah, and so a bunch of data is collected here. In particular, I think something I want to comment on is we did some interviews with patients, AI supervisors, and providers, and I think a lot of rich detail about how they felt about, how the different stakeholders here felt about that. And I think it's quite interesting to look through in the paper. Yeah, so in terms of participation and safety, so 140 verbally consented to participation. There were some amount that started the encounter but had reasons for not completing the encounter, which were not considered safety terminations. So some of them were, we had pre-specified that this must be happening on a web interface and they were using mobile phones. There were a few instances where the agent itself was unavailable due to the technical serving constraints that we were operating under. And there were 2 patients that were excluded due to meeting the exclusion criteria that was not immediately known, but during the conversation it became known. And this was a reason to not continue with their encounter. So there's 100 that completed the AMIE encounter. 2 of these did not show up to the PCP encounter. Those were followed up with for safety reasons to make sure there was no issues.
So they are physicians, they are open to the physical exam and to the interview at the same time, and they can kind of inform each other.
Yeah.
But here, the AI, they only can do the interview. Right?
Yeah.
So then, how do you handle that?
Yeah, so in their subsequent PCP encounter, they will be able to do the physical exam because that's an in-person encounter. In this chat, obviously there's no physical examination. So the AI must, provide whatever it can with the information it's able to extract in a text interface. Yeah, and here's the demographics of the folks that were there. And yeah, looking at, I think the clinical reasoning performance here, in terms of management differential is promising. I think, one really important thing where we did not do as well on was the practicality and cost effectiveness of our management plan. So this sort of reflects the, I think, real world understanding of, in particular this practice, but in general, our system lacks any context around, what actually happens at this practice. And for that reason, I think it was rated, inferiorly to the PCPs on these axes. For the rest, it was, statistically equivalent. And in terms of top diagnostic accuracy, these line up pretty well with what we saw in simulated settings. And there are some differences between, conditions where the final diagnosis required some diagnostic test versus conditions where the final diagnosis was based on, basically what the PCP said at the end of their consultation. And this one I think is like very exciting actually, because this was based on the surveys done with the patients, where we basically assessed their view of the AI and their trust in the AI. And there was some hesitancy prior to the interaction in some cases, but overall, on average, post interaction, they were happy with the experience, and their trust in the system and AI in general did improve. And I've shown similar plot before, but both from the patient perspective, clinician perspective, AMIE was rated fairly favorably. Yeah, and both from the patient perspective and the clinician perspective. So future directions, again, this is pretty limited scale. So one direction is getting real evidence at scale, where we can unearth the longer tail of medicine. Another is moving from a text interface to real-time audio-video interaction. And finally, understanding how this works as actually part of a real clinical system and a real clinical team, and integrating information from the EHR, for example. In conclusion, through this work, we've built towards meaningful evaluation of medical AI. We have shown some promise in this domain, but much is still unknown. Thank you.
We have another meeting coming up, but quickly, anything last minute question? No, I think that's.
Question, it's referred to the first plot you show is AMIE only, this show a much higher than AMIE plus. The provider, basically the clinician, after look at any result, the performance, which is very interesting. I wanted to know in your study design, did you show that things, because we always think AI will be a tool to help clinician to make a better diagnostic. Would you consider that comparison is AI versus AI plus clinician, other than AI versus clinician?
Yeah, in this study, we didn't look at that particular combination. I do agree that's quite interesting, and I think there's some question. Like, I think one reason for that is there's a lot of open questions about what exactly that collaboration even looks like. We can only propose one thing and test that one thing. In the first study, for example, I think some of the performance differences are not necessarily because we think that AI can't help clinicians or clinicians can't use AI properly, but we can only propose one particular interface and look at one subset of cases. So it's hard to draw, I think, broad conclusions from that.
Oh, all right. Well, thank you very much. Well, that's very interesting. So I think they found it, I should see that people want to actually